Hello everyone, and welcome to the lecture on singly linked lists. In this lecture we'll have an overview on singly linked lists, what they are, we'll see some diagrams to explain them, and then more specifically we'll also go over adding elements to a linked list and removing elements to a singly linked list. Okay, formally and in a general sense, a singly linked list in its simplest form is a collection of nodes that collectively form a linear sequence. Each node stores a reference to an object that is an element of the sequence, as well as a reference to the next node of the list. So if we see this drawn out as just what a single node looks like, we have our element. In this case, we're going to use airport codes as our elements. MSP is the airport code for Minneapolis. And then we have another reference to connecting to another node in our linked list. So we can think of this as a bunch of nodes that are linked together by these pointers. Here we have a more full diagram of a singly linked list. The list instance maintains a member named head that identifies the first node of the list, which is this one right here. Notice how nothing points to the head since it's the first node of that list. In some applications, another member named tail that identifies the last node of the list may be found over at the end. And in this case, this node points to none or nothing, indicating that it's the tail. And remember, each of these nodes, again, it's referencing its own element, in this case, the airport codes. Again, the first and last node of a linked list are known as the head and tail of the list. We can identify the tail as the node having none as its next reference. This process of going throughout the nodes and going through them and checking the linked lists by going through the nodes is commonly known as traversing the linked lists. So just a couple terms to review. We have the head and the tail of the linked list. And if we start going through the nodes and going through the connections of the pointers, that will be known as traversing the linked lists. Because the next reference of a node can be viewed as a link or pointer to another node, that process of traversing a list is sometimes also known as link hopping or pointer hopping. We'll just call it traversing. Each node is represented as a unique object, with that instance storing a reference to its element, in our case, those airport codes, and a reference to the next node, or in the case of the tail, none. So we changed the diagram here just for simplicity's sake, with the reference to the element just being part of the node, instead of writing out that pointer. That way it looks a little cleaner. Now let's talk about inserting an element at the head of a singly linked list. How would we actually go about doing that? An important property of a linked list is that it does not have a predetermined fixed size. It uses space proportionally to its current number of elements. That means to insert a new element at the head of the list, we have to do four things. We create a new node, set its element to the new element, set its next link to refer to the current head, then set the list's head to point to the new node. Let's draw this out in a diagram. Okay, we have three steps here, or three diagrams, A, B, and C. A is what our singly linked looks like before we actually do an insertion into it. So we have the head node, Minneapolis, pointing to Atlanta node, pointing to the Boston node, pointing to none. And now we want to insert an element to the head of a singly linked list. So we want to insert LAX here. After we create the new node, what we end up doing is a reassignment of the head reference. So we assign LAX and reference the next node, Minneapolis, and then do a reassignment of the head reference to LAX. Now we want to insert an element at the tail of a singly linked list. We can also easily insert an element at the tail of the list, provided we keep a reference to the tail node. In this case, we create a new node, assign its next reference to none, set the next reference of the tail to point to this new node, then update the tail reference itself to this new node. Let's see what this looks like as a diagram. Here we have three figures. This first one, A, is what it looks like before the insertion. So we have Minneapolis as the head, pointing to Atlanta, pointing to the tail Boston, which itself points to none because it's the tail. Then we create a new node here in this figure, and after we do this, we set that new node to reference none. It's important to note that we must set the next link of the tail, in this step B, before we assign the tail variable to point to the new node in C here. So we set up our new node and then first point it to none before pointing our previous tail to the new tail node. Now let's talk about removing an element from a singly linked list. Removing an element from the head of a singly linked list is essentially the reverse operation of inserting a new element at the head. Here we explain it through some diagrams. This is what our singly linked list looks like before removal. We have LAX, Minneapolis, Atlanta, Boston, with LAX at the head, Boston at the tail. And we basically just link out LAX by pointing the head to Minneapolis, and then we can easily remove that node. We cannot easily delete the last node of a singly linked list, however. Even if we maintain a tail reference directly to the last node of the list, we must be able to access the node before the last node in order to remove the last node. But we cannot reach the node before the tail by following the next links from the tail. If we want to support such an operation efficiently, we will need to make our list a doubly linked list. So we've learned a lot about singly linked lists and how to add and remove elements from them. Up next, we're going to implement a node class and create a singly linked list. As far as the actual topic of linked lists, formally and through diagrams, you might think, hey, this is pretty simple. It's just a bunch of nodes pointing to each other and then pointing to an element. And I think when you see the actual implementation, you'll realize it is just that simple of an idea. The singly linked lists, you have nodes that point to each other. The trick is just doing certain operations on them, such as reversing them or checking a particular node in that list, or removing nodes from the tail of a singly linked list, in which case you have to go to a doubly linked list. Hopefully you can see in our implementation in the next lecture that this is a pretty simple topic and straightforward. The challenge is feeling comfortable enough with it in order to solve the interview problems that we see at the end of this section. Alright, so let's go ahead and jump to the next lecture where we're going to implement our own node class and create a singly linked list. Thanks, and I'll see you at the next lecture.